Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're looking at Chapter 4, which is on entropy, and today we'll be looking at an entropy balance. So, I call it an entropy balance. The truth is, entropy doesn't balance, right? We've just finished discussing the second law and how it says that delta S for the universe is going to always increase. For a reversible system, we can make it go to zero, but otherwise it's always going to be positive. So how can that balance? What we need to do is define a new term. So entropy generation, S sub GEN, is the entropy generated by those irreversible processes. When you have a reversible process, Sgen is going to be zero, and it's going to be positive for any irreversible process. If ever you do a calculation that finds Sgen is negative, you've either made a mistake in your calculations or the process was impossible. So now, if we write our second law with this Sgen, we get a balance equation. In our textbook, it's 437. But what it says is that the change with time of the total entropy in the system, so mass times the specific entropy of the system, is equal to the sum of all streams coming in, the mass flow rate coming in times the entropy of that stream, the specific entropy, minus the flow of all streams going out times their specific entropies, plus the rate of heat transfer divided by the temperature it's happening, plus Sgen. And that gives us a balance. It's a much more satisfying way to work a problem, even though we had to make up a new term to do it. If we integrate that equation from time 1 to time 2, then we get a term not in terms of rates, but in terms of the mass at the end of the process times the entropy at the end, minus the mass at the beginning of the process times the specific entropy at the beginning, is equal to the sum of all of the accumulated mass that came in times those specific entropies, minus the sum of all the accumulated mass that left times that specific entropy, plus all of the heat transfer divided by the temperature those occurred at. Keep in mind that those have to be absolute temperature, and then we'll add to that Sgen. Again, Sgen needs to be zero or positive, otherwise the system is impossible. So next, let's look at an example. If we have an insulated counterflow heat exchanger, so that is going to tell me, first of all, insulated simply means that all heat transfer is going to happen within the system, not to the surroundings. And counterflow means that one stream is coming in from one direction and flowing the opposite direction of the second stream. So this heat exchanger is going to operate under steady flow. We have liquid water at 15 degrees C, which we called state 1, or I identified as state 1. Coming into our heat exchanger, I've drawn the exchanger here as if it's insulated, so that's what the little hash marks around the side mean. So stream 1 is coming in, it's water, and it's going to leave at state 2. We're going to have a refrigerant, R410A. The names of refrigerants are, tend to be numbers. Remember, this is going to be counterflow, so this stream is R410A. They are not going to be allowed to mix. Okay, it's going to enter at 140 bar, 80 degrees C, and that's state 3, with a flow rate of 5 kilograms per minute. And it's going to leave as a saturated liquid at 50 degrees C, so it's going to come out, well, now. Uh, 50 degrees C, saturated liquid with those properties. We want to determine the mass flow rate of the water stream and the rate of entropy generation due to irreversible heat transfer. So I have two streams. They are not going to mix. So the mass flow rate at stream 3 will also be the mass flow rate of stream 4. And the mass flow rate of my water here will also be the mass flow rate of my water here. And those are rates. So to get started, what I want to first do is write an energy balance. I'm almost always going to do both a first law and a second law analysis on any problem, okay? Now, my energy balance, we've done this type of problem before. There's no heat transfer with the surroundings. There are two streams in and out. There is no work being done, no moving parts in a heat exchanger, and there's no accumulation. So therefore, my energy balance says that the sum of all of the mass coming in times the specific enthalpy in of each of those is equal to the mass coming out times the specific enthalpy going out. And for my specific flow streams here, what I have is that streams 1 and 3 are coming in, and streams 2 and 4 are coming out. Okay, now I know the mass flow rates of streams 3 and 4, M1 and M2 are equal to each other. I named those MW. And I have MW is going to be H1 minus H2, and that's going to equal the mass flow rate of the 410A times H4 minus H3. Now, H3 and H4 were given in the problem statement. For states 1 and 2, I have a snippet of a data table here. This is liquid water at 15 degrees C. They don't tell me anything more about it, so remember that if I have the temperature, really kind of doesn't matter what the pressure is. Those properties will be very much the same. So at 15 degrees C, enthalpy of the liquid is going to be 63. The entropy of the liquid is going to be 0.2245 kilojoules per kilogram Kelvin. And as it exits, it's going to be 25 degrees C. So this is going to be my state 2 values. If I substitute those in, mass flow rate of the water is going to be 5 kilograms per minute times 142.7 minus 350.6 all over 63 minus 104.8. And this is about 25 kilograms per minute. So that got me the flow rate. But next, they want to know what is the rate of entropy generation. So for this, again, if I have no heat transfer with the surroundings and no accumulation, my entropy balance gives me entropy generated is going to be the sum of the mass times entropies out minus mass and entropies in. In this case, streams 2 and 4 are coming out. 1 and 3 are coming in using the data from the previous page. For the streams 2 and 4, the flow rate is 5. Out is 0.5067, in was 1.21. For streams 1 and 3, the flow rate was 25. Out was 0.3672, in was 0.2245. The units on those, the flow rates were in kilograms per minute, and the specific entropy in kilojoules per kilogram Kelvin. So those kilograms cancel. I have kilojoules per minute per Kelvin, which is somewhat unusual units. If I switch my 1 minute is 60 seconds, then I get 1 kilowatt is a kilojoule per second, and I end up with S generated is 3.2 kilowatts per Kelvin. This is positive, so therefore this is an irreversible process. And it's a number. It's a little bit difficult in a silo like this to identify whether or not that's a large value or a small value. And in fact, it's a bit large. All right, that concludes this video lesson. In our next lesson, we're going to be looking at more examples.